Okay. All right. So last time we proved this theorem. It was characterization of compactness using sequences, right? So let me find the statement. Here it is. The following statements are equivalent on a metric space. XD is compact. Every sequence in X has a convergent subsequence. XD is complete and precompact. We proved that these three conditions are equivalent. Okay. Now we will see some consequences of this result today. All right. So okay, the first consequence is the following. Uh, so here is the proposition. The Cartesian product of finite number of compact metric spaces is compact. The Cartesian product of finitely many compact metric spaces is compact. Okay. So what we mean by this is the following. Suppose x1, d1 and x, let's say k, dk be compact metric spaces. So compact metric spaces. Let X be the Cartesian product of these spaces, and rho R R1 greater than, okay, R is something between 1 and infinite, including infinity, defined as follows. So rho 1, remember, was d1 up to dk, rho infinite, rho r for r being larger than 1 was this di to the power r, and then you take 1 over rth root, and rho infinity was the maximum of d1 up to dk. I wrote in short notation, but you understand what's going on. These metrics are equivalent. These metrics are equivalent, and therefore uh, uh, open subset, a subset is open with respect to one metric rho r is open with respect to any of the other metric rho r prime for any r prime. So therefore, no matter which metric you choose on this X, your open sets will not change. Okay, because the distances are comparable. One of them is like 5 times the other one, and so on, because the metrics are equivalent. Therefore, the open sets are the same. Since the open sets are the same, uh, checking compactness with respect to one of them is equivalent uh, to checking compactness with respect to other metric, because compactness is defined via open sets. Therefore, X is compact with respect to row R if and only if it is compact with respect to row R prime uh, for any R prime. Okay, so therefore it is enough to check compactness for only one of them. So let's say hence we may work with any metric we wish on X. Okay, let's work with work with okay D1 or D uh, okay D infinite. Evet. Yok, bunlar norm uzay olmasa da olur. Yani norm olarak düşünmüyorum. Yani dr dediğim şey şu. Dr dediğim şey şu. Toplamları veya e, yani bunlar norm space olmak zorunda değil. X'ler herhangi metrik uzay. Yok, ama burada X'ler norm uzay olmak zorunda değil. O yüzden diyorum. Normdan gelmiyor bu metrikler. Onun için ispat ediyoruz. Evet, evet, evet. Hı hı. Okay, so how can we prove this? So I'll use to prove the theorem. I'll use the characterization to prove the theorem. We use the sequential compactness. So a metric space is compact if and only if it is sequentially compact. So let Xn be a sequence in X D infinite. So this means what? Xn is, of course, what kind of object is this? This is in X, which is Cartesian product, right? So Xn is something like this, actually. This is some A1, AN, AN1, let me say, AN2, and then ANK, where ANI is a sequence in xi di. Okay, in this matrix space. Okay, how can we show that this is a convergent subsequence? So my aim is to show that must show xn as a convergent subsequence. Well, how can we show this? It's very easy now. Since this is uh, a sequence in x, each one is a sequence in xi, but all these metric spaces are compact. Okay, so I have this. The first, if you look at the first components, then you know they have a convergent subsequence. So I will pass to that convergent subsequence, and then I will look at the corresponding sequence in the second metric space. Since that metric space is compact, that subsequence will have another convergent subsequence, okay, in x2, and then I will pass to that subsequence, and then this will continue up to Kate. So each time I will pass to a subsequence of a subsequence, but each time it will be convergent. First, it will be convergent in the first component, then it will be convergent in the second, then it will be convergent in the third, and at the end, all the components of xn will be convergent. And subsequence of a subsequence is always another subsequence. Therefore, at the end, I will have a subsequence of xn whose all coordinates are convergent. Okay, so that's the idea. Okay, so maybe let me do this for so some kind of example. Let me say xn is something like this. Suppose I have only three metric spaces, so a1, okay, an, bn, and cn. So I take k equals 3, only 3 metric spaces. How I will do this? First, I look at the first component. I have a sequence here, and this has a convergent subsequence. Let's say this subsequence is convergent. A2, A5, A8, A11, A20, let's say 109, and A250, and so on. Suppose this is convergent to some number, let's say A0, okay? Well, I look at the corresponding sequence in B. The sequence in B, so B2, B5, B8, B11, B20, and B109, and B250, this may not converge. Okay, this doesn't have to be convergent. This may not converge, but it is a convergent subsequence. Which sequence? I don't know, but something like this. Maybe B8, B11, B109, and B250. Okay, this is convergent because X2 is a compact metric space, and therefore any sequence in x2, right, this is a sequence in x1, this is a sequence in x3, and this is a sequence in x3, has a convergent subsequence. Therefore this subsequence has a convergent subsequence, and suppose it is this one. B0. What about the corresponding sequence in A, in X1? Well, if I look at, this sequence, B8, so it is this one, and then B11, B109, B250. So I will take this subsequence. Well, since this sequence is already convergent, its subsequence will converge to A0 also. So for this indices 8, 11, 109, and 250, and so on, both of them, both A's and B's, are convergent to A0 and B0. Then I'll do what? I'll pass to the third. I will just repeat this procedure. I will pass to the third sequence. So let's say C8, C11, C109, C250, and so on. This may not converge again, but since X3 is a compact metric space, any sequence in X3 has a convergent subsequence. Therefore, this sequence has a convergent subsequence. Which one? I don't know, but say it is this one, C8, C109, and C250. Okay, so, or let's say this one is convergent to some C0. Now, what I have, this sequence C8, C9, C109, and so on is converging to this. C8, this one is convergent to B0, and A8, A109, and so on is converging to B0, sorry, A0. Now I have all subsequence now are converging to something, right? Therefore, now X8, X, so X8 is this, A8, B8, C8, right? And then X109, and this sequence C8, X8, X109, and so on will converge to where? Will converge to A0, B0, and C0. So I started with Xn and constructed a convergent subsequence. This is the proof. Of course, I explained the proof on an example. Sorry about this. I explained the example, the proof on an example, but the proof is the same. If you read the proof, it will be the same. So I will I will leave the uh, details to you. I mean, not details, but writing up the proof. But that's the idea, okay? You have to just deal with subsequence notation. That's it. So this finishes the proof. Any questions so far? If you read the now proof from the book, it will be something really easy. Okay. Do you have any questions? Okay, if you don't have questions, let me continue with the next proposition. So let A be a precompact subset of a compact metric space not compact, complete metric space, then A closure is compact. Okay. Why is that? Well, this is easy. So A is a subset here. A is precompact and X is complete. Okay. And A is precompact. Our claim is this. A closure is also precompact. Okay. Why is that? Well, what was precompact? So precompact was this. Given epsilon positive, I should be able to find finitely many balls with radius epsilon covering a bar. Well, what I know is that A is complete precompact, so I can cover A with epsilon balls, finitely many epsilon balls. But I'll do a trick. I'll cover A with epsilon over 2 balls. All right, so since A is precompact, there are we can cover A with finitely many epsilon over 2 balls. All right, so A is a subset of B. Let's say x1 epsilon over 2, B x2 epsilon over 2. How many of them? Well, I don't know, but finitely many. Okay, let's say x n epsilon over 2. Okay, for some points x1 xn in x. Then we do what? Well, closure of A may not lie here, but I know this. This A is a subset of this, therefore uh, it's a subset of the closed balls, right? Because closed balls contains the open ball with the same radius. Okay, closed balls, I said. All right. But this time where the letter union, this union, the letter union is closed because each closed ball is closed and I have finitely many closed balls because it is the union of finitely many closed subsets. Well, I obtained a closed set containing A. Uh, but this implies that this closed set contains a closure because a closure is the smallest closed set containing A. Therefore, any closed set containing A contains a closure. Hence, a closure is in this union. Okay. And what's the final step? Well, each of these closed balls are contained in the uh, open ball with the radius epsilon. So finally, each b xi epsilon over 2 lies inside b xi epsilon, right? By the definition of these balls. And thus the closure of A is contained in this ball, but that lies inside this ball. So b x1 epsilon, b x2 epsilon up to b xn epsilon. So a closure is contained in finitely many epsilon balls. And this finishes the proof of the claim. Hence, a closure is precompact. So what we obtained is this then. A closure is a precompact subset of a complete metric space. Hence, now a closure is then precompact and complete. Maybe I write this. Okay. On the other hand, a closure is a closed subset of the complete metric space XD, and thus a closure is a complete subspace or subset or subspace, complete subspace. Therefore, a closure is both complete and precompact. Finally, a closure is compact because it is both complete and precompact. And that's one of the equivalent forms of compactness, right? As a space is compact if and only if it is complete and precompact, right? So this finishes the proof, okay? This is the characterization theorem by the sequential characterization theorem, right? We proved this theorem, remember? Yeah, right? So these conditions are equivalent. XD is compact if and only if it is complete and precompact. I apply this to the subspace A closure, right? A closure is a pre-compact and complete space. Therefore, it is compact. Okay. Okay. Another important result is this. An application of this. This is known as also, you know this from advanced calculus, Heine-Borel theorem. It characterizes compact subsets of Rn. And here is the statement: a subset of Rm is pre-compact if and only if it is uh, uh, bounded. Therefore, uh, as a consequence, a subset of Rm is compact if and only if it is closed and bounded. So for Rn, of course, we take any of the equivalent metrics. So here on Rn, I take which metric? Let's say the R metric. And what is this? This is just okay. So let's say x, y. This is just xi, yi, art power I from 1 to n, and then you take 1 over art root. So r from 1 to infinity, and r infinity for r equals infinite. Of course, this is just the maximum of x1, y1 up to xn, yn. Okay, I use this matrix. Okay, it doesn't matter which one you choose. All metrics are equivalent. Therefore, if it is compact with respect to one of them, it is compact with respect to all of them. All right. My first statement is that a subset is pre-compact if and only if it is bounded. Okay. Let me use this metric. Let's work with the infinity metric. We already know that. Okay, so let A be a pre-compact subset of Rn with this the infinity metric. We already proved that before. We have proved earlier that A is bounded. Okay, this was proved already. Now we proved the converse. Now assume that A is bounded. Okay, I want to prove that A is pre-compact. Must show A is pre-compact. All right, how can we do this? Well, since it is given that it is bounded, there is a ball containing A. Since A is bounded, there is some ball, let's say with center at the origin and radius, let's say uh, big R, so that A is contained in this ball. But what is this ball in this metric? So BOR is this. This is the set of all x's in Rn so that the distance between in the D infinity metric x and 0 is less than R. What is this distance? D infinity x 0. So this is just maximum of what? X1 minus 0, x2 minus 0, up to xn minus 0. Here x is the n tuple x1 up to xn, right? So maximum of this is 0, is the metric. And what uh, our ball is this. All these expressions, absolute values, are less than R. So this is, of course, equal to maximum of x1, x2, xn. Okay. What kind of object is this? Well, this is actually nothing but the following. Uh, in one dimension, it is just this ball. 0 is here, and then I go R unit like this. It is this thing in one dimension. In two dimension, it is the following. Here, this is R minus R minus R and R. Let me put the coordinate axis also. So I have this. Okay. So these are Rn minus R, Rn minus R. So my ball is this. Okay. And in three dimension, it will be the cube actually, with whose sides have length 2r and so on. And my subset A is a subset of this ball, right? Because A is contained in this ball. A is contained in this ball means what? A is somewhere here. Okay, this is A. Well, clearly this ball is contained in finitely many epsilon balls, right? Here epsilon balls, let's say in dimension 2, if n is equal to 2, epsilon balls are just squares. A is contained in this big square, but I can always divide this square into smaller squares, right, of any size. You give me the size of the square, I can divide this into small squares of that size, and it will cover the whole uh, big square. Now, so let me just write it down. Now, if epsilon is given, uh, consider the squares uh, of uh, okay, the form. So in one dimension it will be like this. Okay, 0 is here, let's say r and minus r. I will uh, divide this into epsilon uh, intervals, epsilon here, 2 epsilon, 3 epsilon, okay, minus epsilon, minus 2 epsilon, minus 3 epsilon, and so on. And then I take epsilon balls around each this gadgets, this blue dots. Certainly finitely many uh, balls will cover, epsilon balls will cover this, right? So my first ball will be this, and then my second ball will have center epsilon, so it will be this one. Okay, or maybe this one. And then I'll choose a third ball around this point and so on. So what I mean is this. Clearly, clearly, uh, um, the balls, which balls? So B with center K epsilon and radius epsilon uh, covers uh, this ball 0 r, where what is k? K is a integer, positive integer, so that k times epsilon is larger than r. I choose, so kr is somewhere here, k epsilon. I choose some integer so that k times epsilon is larger than this. So this ball k times epsilon will be a little bit larger than r. So if I just take all these balls, okay, this is the first ball, second ball, third ball, and so on, and then I'll go in the negative direction. Those balls overlap some parts, but they all cover, uh, you know, this big ball. Maybe I just write like this. Therefore, they will cover A. Uh, for dimension 2, I'll just have to, pick my centers a little bit more carefully. So here is R minus R, R minus R. So here what I will do, I'll just divide each axis or the part of the axis between minus and minus R and R into this epsilon intervals. Okay, so I'll do this epsilon intervals, and also here I'll do this for each axis, and then I will look at this points, okay, and then consider around each of these points epsilon balls. So what I will do, I'll just actually take these balls and maybe just take Cartesian products of these balls. So okay, so okay, so just take epsilon balls around each uh, you know uh, dot. Okay, red dot. uh, they will cover this ball. So this is what I'm doing, and there are finitely many of them. So around this point the ball will be something like this. Around this point the ball will be something like this. Let's say this point. So okay, around each red dot I'll take these balls, epsilon balls. There are only finitely many of them. How many of them? Well, here I had let's say 2k balls, right? K balls in this direction, K balls in this direction. So at most 2k balls. Here I have 2k intervals in this direction, 2k intervals in this direction. So 2k times 2k, so 4k squared balls, and so on. In 3 dimension, I'll take the third direction and so on. Uh, hence, so this way we conclude that XD, sorry, A uh, is covered by finitely many epsilon balls, so that A is precompact. Well, so what we proved is the following: for a subset of Rn, being bounded and being precompact are the same, and we know that Rn is complete metric space, therefore any subset of it is complete. So a subset, hence for a subset A of Rn, we have this. A is bounded if and only if A is precompact, and since Rn is complete, also since Rn is complete, because R is complete and therefore its Cartesian products are complete. Since Rn is complete, this subset is complete, is closed if and only if A is complete. So if you combine these two statements, okay, I have these two statements here, closed and bounded, and on this side these are equivalent to saying that A is precompact and complete. So A is bounded and closed if and only if it is precompact and complete. But we know that if a space is precompact and complete, then it is uh, compact. So this finishes the proof. Okay, this finishes the proof. Okay, any questions so far? All right, then let me stop now for a break.